In this video, we'll discuss the general approach to finding field configurations in a cylindrical waveguide. What we mean by a cylindrical waveguide is some kind of tube where one can take some cross-section, and it can be arbitrary, and then you translate it normal to itself, and then you have a tube that is a cylinder. The tube is metallic, and the walls of it are sufficiently thick, much thicker than the skin depth, so nothing leaks through. And we're interested in finding the field configurations inside the tube. Now, in reality, of course, a tube like this would be attached to something on the ends, or maybe an end can be open and it could be used in some device like a magnetron or a radar. But we will just treat the area of the tube that is translationally invariant. So we'll find the field configuration in a portion where it looks like a cylinder, and then if it needs to be attached to something else, then there will be an additional boundary condition problem that we will not be dealing with. Of course, we know that each component of the E and B fields satisfies the wave equation. So we can write del squared plus mu epsilon omega squared acting on either E or B. Any component of it should give 0. And we also know the boundary conditions. We will use the boundary conditions for a perfectly metallic waveguide with conductivity tending to infinity. So that will be the tangential component of the electric field at the surface of the waveguide being 0, and same thing for the normal component of the magnetic field. Now, the problem with these equations is that they're not independent. So the equation for each component is sufficiently simple, and we have the boundary conditions, but they are coupled through Maxwell's equations. The curl equations have to be satisfied, so different components of E and B fields are talking to each other. So that is something that needs to be built into the solution. So the goal of this video is to develop a convenient way to do this. The first thing we note is that because of the translational invariance along the axis of the waveguide, let's introduce an axis z parallel to the axis. So because of this translational invariance, we can look for solutions for the fields in terms of plane waves with respect to the z direction. So we can represent the fields as this, with e to the ikz exponent, and same thing for the B field. So we have amplitudes that depend on the location in the cross-section, x and y, but the z dependence is given by the e to the ikz factor. Now the reason is that if we substitute these solutions into the wave equations, then and in the Maxwell's equations, we'll find that the solutions with different values of k don't talk to each other. This is because the differential operators don't change the z dependence for this exponent. The x and y derivatives don't act on the e to the ikz factor at all, and d by dz just generates an ik factor, so it's algebraic. And on top of this, the boundary conditions are independent of z. So there's nothing that can couple the solutions with different values of k. In order to proceed, we're going to split the axial and transverse components of the fields and of the differential operator. We start by writing the Laplacian as the sum of the transverse part that involves derivatives with respect to x and y, and the axial part, d2 by dz squared. If we apply this to the fields written in this form and substitute into the wave equation, we'll get something a bit simpler that contains only the transverse part of the Laplacian. And here we have mu epsilon omega squared minus k squared. So that's the result of acting by the d2 by dz squared operator. And then here I have E and B fields. And now, because nothing on the left acts on the e to the ikz factor, these equations apply just to the amplitudes that depend on x and y only. So this is now, instead of a three-dimensional differential equation, it's a two-dimensional. The functions and the operators depend only on x and y, and we've taken care of the z dependence. I can emphasize that by explicitly showing that this is only the EXY and BXY amplitudes. Now here comes the key point of the following derivation. We will see that we can solve this equation for the axial component of either E or B with the corresponding boundary condition, and we'll find two different kinds of modes depending on whether it's E or B that we're looking for. And then we'll recover the transverse components of both E and B fields from either E sub z or B sub z. We will find out how to do this in the rest of this video. Our strategy will be to separate the transverse and axial components of the fields. So we'll start by writing for each field E, for example, would be E transverse plus the axial part. E sub z is the axial part. And then we'll separate the transverse and axial components for all the Maxwell's equations. To see how this works, let's start with the Maxwell equation for the curl of E. So curl of E is negative b dot. So for the complex amplitudes, that gives us I omega b. So now we substitute the fields written in this form, and we use this form for the del operator as well. So we would write del as del t, that's the transverse part, plus del z. This Maxwell equation then becomes del t plus del z crossed with et plus z ez equals I omega b transverse plus b axial. Now we want to separate the axial and transverse components of this equation. To do this, we can either dot it with z, that will give us the axial component, or we cross it with z. That will destroy the axial component and leave all the transverse one. So first, let's see what happens with the first case, when we dot the equation with z. Here we have a mixed product, so three vectors, and none of the two can be collinear. So because we have z in one of the three vectors, we cannot have a axial vector in any of the other two. So this means this part drops out and this part drops out. So what remains is just z dot del t cross et equals I omega bz, because crossing, dotting with z destroys the transverse part. So this is the first equation that we obtain. Now let's look at the other one, where we cross this expression with z. So on the left-hand side, we have a double cross product. So we can call this A, the del operator as B, and the field as a C, and we apply the back cab rule. Now we need to keep the field to the right of the differential operator, but we don't need to worry about z. Z is a constant vector, so it doesn't matter whether it's to the right or to the left of the del. So in the back term, we simply get del t plus del z, and ac is z dotted with a field, so that's just ez. And the cab term gives us minus d by dz et plus z ez. The right-hand side gives us I omega, and I have a z cross with the field, so that gives us z crossed with b transverse, and the term with bz is destroyed. Here we see that the terms with dez by dz are identical and cancel out. I've transferred the two equations that we found to this next slide. So let's now deal with the curl equation for B. So we'll do it in exactly the same fashion. So I have another Maxwell equation for curl B. And again, I split the vectors in two parts. So I'm going to write del t plus del z crossed with bt plus z bz. And on the right-hand side, et plus z ez. And then I take that and I dot it with z, and I cross it with z. So from the dot with z, again, as before, the z components of the other two vectors drop out. So I find z dot del t cross bt equals minus I mu epsilon omega ez. The dot with z destroys the transverse part. And when I cross with z, I find del t plus del z bz minus d by dz bt plus z bt. The right-hand side is minus I mu epsilon omega z crossed with et. Now the axial part has dropped out. Here again, the z components on the left, dbz by dz, cancel out. And we add these two equations to the ones we already have. Finally, the divergence equations are handled rather trivially. So I have del t et plus dez by dz equals 0, and a similar equation for B. So here we have completely rewritten all the Maxwell's equations with the transverse and axial parts as separated. In fact, for the following, we'll just need two of them, this one and this one. As mentioned before, we would like to express the transverse fields in terms of the axial ones. So we need to eliminate either a B transverse or E transverse from these expressions. First, notice that d by dz always returns just ik, no matter what amplitude it is applied to, because of the assumed e to the ikz dependence on the z coordinate. So I can substitute ik instead of d by dz in both equations. So let's eliminate b sub t from these two equations, so we can find an expression for E transverse as a function of axial Ez and Bz. So here, in the first equation, Bt enters as Z cross Bt, and in the second equation is just Bt. So what we can do is take the second equation and cross it with Z. Then the term with Bt here will have the same form as the term in the first equation, and then we can just subtract one from the other and eliminate it. So let's call this equation 1 and equation 2, and I'm going to take equation 2 and take a z cross with it. So I have z cross del t bz minus ik z cross bt. And here I have on the right hand side z crossed with z cross et. Now, using the back cab rule, the back term is 0 because z is orthogonal to et. So this gives me minus et. Very simple. So the right hand side is I mu epsilon omega et. And let's also multiply this equation by omega. Now I take equation 1 and multiply it by k, and I take z cross bt and write it on the left. So I write it as I, so I multiply by k omega z cross bt. I'll keep the ez term on the same side with the bt term. So I'll have minus k del t ez, and the other term will stay on the right hand side. So I have minus I k squared et. Now the terms with bt are identical and have opposite signs. So I take these two equations and I add them together. So what I find, let me just write the expression for e sub t. So that's on the right hand side. I have I mu epsilon omega squared minus k squared e sub t. The terms with bt have cancelled. And here I have omega z cross del t bz minus k del t e sub z. Let's rewrite this slightly by multiplying by minus I, and let's save this equation. We can use the same method to eliminate e sub t to find b sub t. So in order to do this, we simply take the first equation and cross it with z, and then the z cross e sub t can be combined with z cross e sub t in the second equation and eliminate it. So if we do this, we'll get a very similar expression for b sub t. So these last two equations allow us to find e sub t and b sub t if we know e sub z and b sub z, as long as the factor on the left in the brackets does not vanish. Okay, let us now retrace our steps a little bit and make the following observation. So previously, we found that all the Maxwell's equations can be written in the form where axial and transverse components of the fields are separated, and that set of equations looks like this. So there were 6 equations, 4 of them following from the curl equations and 2 from the divergence equations. Then we picked this pair that gives us the transverse components, and we combined these two to obtain this pair of equations. So this pair is equivalent to these two. Now we also know that all components of the fields, both electric and magnetic, satisfy the wave equation, which is itself derived from Maxwell's equations. Let us keep just the axial components of the wave equations. Now it is clear that if the axial components of the fields do not all vanish, which means the right-hand side of these equations is not 0, then the bracket on the left cannot be 0. Otherwise, the transverse fields E sub t and B sub t would diverge. Now, if that is the case, if this bracket does not vanish, it is straightforward to show that if the wave equations for E sub z and B sub z are satisfied, and these two equations are satisfied, then the other four of the 6 Maxwell's equations here are satisfied automatically. They turn into identities if both wave equations and this pair is satisfied. So we can drop these from further considerations if the axial fields do not all vanish. The structure of these equations tells us that there are two kinds of solutions with non-zero axial fields, either electric or magnetic. So first type would be the solution where the axial electric field is non-zero and the magnetic field is zero. The other type would be zero electric field and non-zero magnetic. The first type is called transverse magnetic because the magnetic field is purely transverse. The other type is called transverse electric. They're also commonly denoted Tm and Te. To find those solutions, one starts with a wave equation, either for E sub z or B sub z. There are different boundary conditions corresponding to them, and the solution of this equation gives us an eigenvalue problem. Once we find E sub z or B sub z, we can substitute them in this equation. So for the Tm modes, you substitute E sub z. For the Te modes, you find B sub z, substitute here, and find the transverse fields. The third type of solutions that is possible in some types of waveguides that needs to be considered separately is a solution where both electric and magnetic fields vanish. Now, this is only possible in combination with the equality mu epsilon omega squared equal k squared. Because if both axial fields vanish, the left-hand side has to vanish too, and that can be only guaranteed if the bracket is zero, because the transverse fields cannot vanish identically. Notice that this dispersion relation is the same as plane waves have in a infinite medium with the same mu and epsilon as the interior of the waveguide. This mode is called transverse electromagnetic, and it needs to be considered separately. Let us finally establish the boundary conditions for the wave equations for the axial fields. The case of the axial electric field is easy. We know that the electric field has to be purely tangential on the surface of a perfect conductor. The axial component of the electric field is tangential to the surface. So we automatically have that Ez has to vanish at the surface. Now, because here we have a function of two variables, this means we're dealing with the field in a cross-section. So it depends only on x and y. So the surface here is in fact a line, the boundary of the cross-section. Now for the magnetic field, it's a little bit more complicated. So we know that the magnetic field has to be purely tangential to the surface. So the normal component of the magnetic field at the surface of the conductor has to vanish. Now if we use n as the surface normal to the surface of the metal, then n dot b must be 0. To proceed, let's take this equation that we have derived before and dot it with n. So I'm going to take this equation and project it onto the surface normal. The term with b sub t here is simply equal to I k b sub t. And when we dot it with n, it will give 0, because b sub t dotted with in gives us the normal component of the magnetic field, which has to vanish at the surface. So when we take this equation dotted with in and evaluate it at the surface, this term vanishes. The term on the right-hand side here contains Z cross E transverse, and we dot it with in. We can rewrite this as N cross Z dotted with E transverse. Now, N cross Z has a tangential direction to the surface. N is the surface normal, Z is the axial unit vector. So N cross Z is the transverse unit vector tangential to the surface. So dotted with ET, that gives us the component of the electric field parallel to the surface. Now we know the parallel component of the electric field at the surface has to vanish. So this is also 0. So this tells us that the left-hand side, the term with del T Bz dotted with in, has to vanish at the surface. Now n dotted with del T Bz is simply the normal derivative of Bz. And at the surface, it has to vanish. So while the boundary condition for E sub z is of the Dirichlet type, the boundary condition for Bz is of the Neumann type. So dBz by dN at the surface is equal to 0. So we have two different types of eigenvalue problem with the same differential equation for transverse magnetic and transverse electric modes. For transverse magnetic mode, we use the Dirichlet condition, and for transverse electric, we use the Neumann type. Let us denote this bracket here as gamma squared. Then the eigenvalue problem can be written as del T squared plus gamma squared. And here we have a function psi, whose meaning is either E sub z or B sub z, depending on the boundary conditions, either Dirichlet or Neumann type. Thus, we're dealing with the eigenvalue problem of the two-dimensional Laplacian operator. Now, all eigenvalues of the Laplacian operator for both Dirichlet and Neumann boundary conditions are negative. That means that the values of gamma squared for all solutions, both transverse electric and transverse magnetic, are positive. We can assign an index, let's call it lambda, to each eigenvalue, and then that eigenvalue determines the dispersion relation for the corresponding waveguide mode. So what we found is that mu epsilon omega squared minus k squared is equal to the corresponding value of gamma for each mode. This gives us omega squared equals 1 over mu epsilon k squared plus, let's call it omega sub lambda squared, where omega sub lambda squared is equal to gamma sub lambda squared over mu epsilon. 1 over mu epsilon is the speed of light in the waveguide material. If it's filled with vacuum, it's just the speed of light in vacuum. This dispersion relation differs from the dispersion relation in vacuum by the presence of the cutoff frequency omega lambda. Why do we call it cutoff frequency? Well, if we plot the function omega of k, it will look like this, with the intercept on the omega axis given by the cutoff frequency omega sub lambda. This mode can propagate only at frequencies above the cutoff. Below the cutoff, the mode still exists, but the wave vector is imaginary, so it becomes evanescent. Of course, the eigenvalue problem has an infinite number of eigenvalues for both types of boundary conditions, so there's an infinite number of transverse magnetic and transverse electric modes with different cutoff frequencies. In applications, it's usually advantageous to excite only one waveguide mode. So that means that the modes with the lowest eigenvalues, the lowest cutoff frequencies, are the most important. To complete the full prescription, let's return to the transverse fields. First, we notice that the factor on the left-hand side is just the eigenvalue, which is always positive and therefore non-zero. And then we see that for each particular mode, which is either Tm or Te, the right-hand side in both equations contains only one of the terms, the other one being 0. For the transverse magnetic modes, those are the terms with axial electric fields, E sub z. And E sub z is our eigenfunction psi. We can rewrite these two expressions like this, where we have introduced the mode impedance denoted by capital Z. Note that the impedance depends on the frequency and not just on the eigenvalue. And for transverse electric modes, we can find rather similar expressions with a different definition of the impedance. The eigenvalues and eigenfunctions of the Laplacian, of course, depend on the shape of the waveguide's cross-section, and they need to be found separately in each particular case. The case of transverse electromagnetic waves, which is possible in waveguides with a cross-section that is not singly connected, also needs to be considered separately. This concludes this video on cylindrical waveguides.